gravimeters that we use have a sensitivity of roughly 0.001 milligauss, or 10 to the minus 9 of the force of gravity. Really sensitive instruments. They have to be sensitive because density contrasts are not that large, and they can occur relatively deep, which means this R squared term can actually override the effects of gravity. So what would be an example of a spring gravimeter? A sheet spring gravimeter would be a scale. Okay. Well, we can be a little bit more sophisticated than a scale. First of all, what does a gravimeter measure, and what does a scale measure? A gravimeter measures the local vertical component of the combined gravitational and Earth rotation acceleration fields. And it also, if there were a pull of gravity to the side, it would also measure only the vertical component. So as an example, suppose you had a pull of an excess body. You've got the pull of the Earth, which is vertical. The combined pull is some angle from the vertical, so you have to take the projection of the combined pull and project it along the vertical. Okay, so what we're doing in measuring gravity is we're basically measuring the displacement of a spring given a force on a mass, just like a teeter-totter. So we can write the relationship between the spring constant and the mass as a ratio, right? Ks, or K is the length of the spring, is Gm. The force going down has to be balanced by the length of the spring using Hooke's law. So we can also say that K over M is the change in gravity over S. And so the change in gravity, the percentage change of gravity, is also equal to the percentage change in the length of the spring. Notice that in this case we need to measure the spring displacement in accuracy relative to the length of the spring. So we need a really long spring to get gravity precision. And you can't use a short spring with this kind of configuration. Well, what does that do? That really screws us up because we've got to have, you know, a giant, giant tube to measure gravity accurately. And I apologize for the picture, but if you can look up zero length spring. So this spring right here we call a zero length spring. And in this case, if you measure the change in length of the spring relative to the change in gravity, you will find that the maximum sensitivity is no longer a longer spring, but the maximum sensitivity that you get is actually an infinitely short spring. So this configuration actually allows you to measure gravity extremely accurately with an extremely short spring. And a modification of this is basically what is used in gravimeters, these land gravimeters today. And so this is a picture of a typical land gravimeter. You have a short lever, you have a long lever, a hinge, a beam. Here's your zero length spring that creates a motion in this position that is read by the meter at the surface. Now it's very, very important in gravimeter surveys to get the gravimeter level. You basically want that gravimeter, just like a plumb bob, to be extremely level. So there's a very sensitive plumb bob or bubble in this gravimeter that makes sure you're extremely level. Pardon? Why is it used an extremely short spring? Oh, because in this configuration, and I can show you the map of this as well, I'll do that next time. An extremely short spring actually gives you more sensitivity, okay? When you have a rotating beam like this, you can actually get more sensitivity to gravity with this configuration, or more sensitivity to the change in gravity. So here's a surface picture of micro Lacoste. And like I said, these things are sensitive anywhere from 10 to the minus 12 to 10 to the minus 9 of the force of gravity, or about 0.001 milligrams. So the gravimeter itself, believe it or not, is not the limiting factor in how accurately we can measure gravity. And I'm going to go over this. I'm actually going to jump around here a little bit. But what I want to look at first are elevation corrections. All right, so when we have a measurement along, let me go back here. Sorry, this is a little bit disorganized. Let's say that we're making gravity measurements along a surface that is not flat. What we would like to do is correct those to this ellipsoid, right? Where we assume, other than anomalies of density, that we've got a constant gravity. So what we're going to have to do to get roughly r squared constant is, over areas where the land is higher than sea level, we're going to have to correct that down to sea level. And other than areas like Death Valley, we're always going to be basically moving our point of reference down. Okay? So if we're moving our point of reference down, what are we doing to our gravity measurement? So if we measured gravity up at the top there, we'll call that an observed gravity. We'll talk about that in a little bit. So if I'm moving my measurement down, what am I doing to gravity? Increasing it, right? So that correction right there, moving it down to a reference, is called the free air correction. And we can calculate what that free air correction is. If we want to change gravity, looking at the change of gravity as a function of r, we have to take the derivative of gravity with respect to r, which gives us minus 2gm divided by r cubed, which is simply minus 2g over r. And that turns out to be 0.3086 milligals per meter. So this is the value that we need to add to put our reference frame at sea level. So let's just write that out as a definition. So we'll do a picture first. Sea level. And this is the measurement point. Observed want to get an accuracy of 1 milligal, what we do is we say, okay, 0.1 milligal equals 0.3086 DH. DH is the accuracy that we need to know the elevation. So we need an elevation accuracy DH. We divide this by that, 0.1 divided by 0.3086. That's about 0.03 meters or 3 centimeters. Really accurate measurements to get an accuracy of basically